Hello and welcome back. This is our last video on atomic scientists. Please take out your handout so we can start taking notes on the work of Louis de Broglie. Louis de Broglie has a very long name too, as other scientists do. His complete name is Louis Victor Pierre Raymond, the seventh Duke of de Broglie, and I know it looks like it's pronounced DeBroglie, but it's actually pronounced de Broglie in French. He was born in 1892 in Dieppe, France, and he died in 1987 in Louveciennes, France. He was a physicist, and he developed the theory of wave-particle duality. This theory was actually his PhD dissertation, which was written in 1924, and he titled it "The Research on the Theory of the Quanta." Years later, he was awarded the Nobel Prize in Physics for this same research. In 1923, de Broglie proposed a hypothesis to explain the theory of atomic structure, and he based his hypothesis on Einstein's work on the photoelectric effect. So the question he asked himself was, if light has both wave-like and particle-like properties, shouldn't all matter have these properties as well? Here we have a picture of de Broglie and Einstein, because Einstein's theory contributed greatly to de Broglie's theory and was a proof that waves and particles could overlap. So light can also be observed as a particle, which is known as a photon, which is the particle that we have here. This comes from light. And when light is shown on a certain object, for example, this atom, the electrons will be released. However, we do need a certain amount of energy for these electrons to be removed from the atom. In this illustration, we have a photon that's emitted. This comes from light, and if this photon doesn't have enough energy, the electron will not be emitted from the atom. So we need enough energy from the photon to actually emit an electron. Here we have the duality of light that Einstein proposed. Light can act as both a particle and a wave, and sometimes it will act as a wave. That means that it will have a characteristic frequency, a wavelength, and an amplitude. And when it acts as a particle, it will contain discrete photons or packets of energy. These photons are the particles of light. Now I want to show you how de Broglie derived his equation for wavelength. So he starts using Einstein's equation relating matter and energy. E stands for energy, M will be the mass, and c is the speed of light. Then he uses Planck's equation based on Planck's quantum theory that every quantum of a wave has a discrete amount of energy given by this equation. E again stands for energy, H will be Planck's constant, which is right here, and nu, this is nu, it's not a letter V, it's the Greek letter nu, will stand for frequency. Now, because de Broglie believed that waves and particles had the same traits, he made both of these equations equal to each other. So that's why we have Einstein's part is equal to Planck's part. And then, because real particles do not travel at the speed of light, de Broglie substituted the speed of light with velocity. So that's the change we see from here to here. We no longer have c squared, we have velocity squared. Now, through this equation, we're going to substitute velocity over lambda, this is the wavelength, for nu, and when we do that substitution, we arrive to this final expression, which gives us the equation for wavelength. De Broglie never proved his model. He didn't have any experiments. He only did a mathematical model of what he thought the atom would look like. But he didn't do experiments like J.J. Thomson did or like Rutherford did. And finally, here we have de Broglie's atomic model. His theory is basically that electrons behave both like waves and like particles. And here we have the dashed lines, the dashed circles here will represent the wave movement of these electrons. And what we have here as a clear orbits in the back will be Bohr's orbit. So this is just for us to compare Bohr's model and de Broglie's model. So we have the different energy levels, and this, however, will mean the that this behave as waves and not as well, they can also behave like particles, but we have this duality. We have the particle part and the wave part within the same atom. Now I want to show you a very cool video from Dr. Quantum, and he will explain an experiment that actually explains de Broglie's model. So even though de Broglie didn't do the experiment, scientists after him did, and this experiment, it's very helpful to see how something can behave both as a wave and as a particle. So thanks for watching, and I'll see you in class.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peep and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands. not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer